Deep within a black hole, time itself grinds to a halt. This is not science fiction, but the startling prediction of modern physics. These cosmic giants warp reality so completely that they challenge everything we know about the universe. By the end of our journey, you will understand how the physics inside a black hole's core could rewrite the fundamental laws of nature. We will venture into a place where gravity becomes infinite and where the very fabric of space and time may unravel. What does it truly mean to stand at the edge of a reality where the rules no longer apply? A star's final moments are a violent and beautiful farewell. When a massive star, one many times heavier than our own sun, burns through the last of its nuclear fuel, the delicate balance that sustained it for millions of years shatters. For its entire life, the outward push of nuclear fusion fought a constant battle against the star's own immense gravity. Once that fire goes out, gravity wins in an instant. The star's core, no longer supported, collapses catastrophically inward. In a matter of heartbeats, an object the size of a giant star is compressed into a point of near infinite density. This is the birth of a singularity, a place where the laws of physics as we know them cease to apply. The energy released in this collapse blasts the star's outer layers into space in a brilliant supernova explosion, outshining entire galaxies for a brief, spectacular moment. What remains is the stellar corpse, a black hole. The matter that once made up a colossal star is now crushed into a region of space so small it defies common sense. An object with the mass of our Sun would be squeezed into a sphere less than 4 miles across. This unfathomable density creates a gravitational pull so powerful that not even light can escape its clutches. The boundary marking this point of no return is called the event horizon, a one-way door from which there is no coming back. This invisible boundary is a one-way street for the laws of physics. Once you cross the event horizon, the cosmic traffic rules flip entirely. The escape velocity, the speed needed to break free from a gravitational pull, here exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing, not a single particle or a whisper of information, can ever come back out. It is the ultimate point of no return. Yet the event horizon itself is not a solid wall you would crash into. It is a mathematical line in the fabric of space, a place where gravity's grip becomes absolute. If you were an astronaut falling toward a black hole, you would not feel a sudden jolt as you passed this threshold. From your perspective, you would simply fall inward. But for anyone watching you from a safe distance, a bizarre cosmic illusion would unfold. They would see you slow down, as if moving through thick syrup, your image becoming redder and dimmer until you appeared to freeze completely, forever etched on the edge of the black hole. This is not magic, but a direct consequence of how immense gravity warps time itself. The light you emit struggles to climb out of the gravitational well, stretching into longer, redder wavelengths and taking progressively longer to reach the outside observer. They witness your time slowing to a crawl relative to their own. But what does this frozen image from the outside tell us about your reality on the inside? For you, time flows forward normally and the core's pull is irresistible. The event horizon is merely the gateway. Beyond it, space becomes a relentless current, flowing inward toward the heart of the darkness. Einstein's great insight was that space and time are not separate. They are woven together into a single fabric called spacetime. Think of spacetime as a vast, flexible sheet. When you place a heavy object on it, like a star or a planet, the sheet dips. That dip, that curvature, is what we experience as gravity. The Earth orbits the Sun not because of some mysterious force pulling it, but because it is following the curve in spacetime created by the Sun's immense mass. Now take that idea and push it to the absolute extreme. A black hole is not just a dip in the sheet. It is a puncture, a well so deep and so steep that its walls become vertical. This is where the universe's rules are rewritten. As you approach a black hole, the curvature becomes so severe that even light, which travels in straight lines, is forced to bend its path. This is why black holes are invisible. They trap the light that would reveal them, but the warping does not stop with light. If you were falling feet first toward a black hole, the gravity at your feet would be unimaginably stronger than the gravity at your head. The difference in pull would stretch you into a long, thin stream of atoms. Physicists call this spaghettification, a dramatic name for a truly dramatic process. Yet the most profound effect of this curvature is not on space but on time. Just as the fabric of space is stretched, so too is the fabric of time. A clock closer to a strong gravitational field ticks slower than a clock farther away. This is gravitational time dilation. Near the event horizon of a black hole, time slows to a crawl relative to the outside universe. For someone falling in, their watch would appear to an outside observer to have nearly stopped. This is not an illusion. It is a fundamental property of a universe where space and time are one. This extreme slowing of time is the prelude to the ultimate mystery. What happens when you follow that river of curved space all the way to its end, to the place where time itself is predicted to stop? The slowing of time you witness from the outside is a mere whisper of the strangeness within. For the astronaut crossing the event horizon, time continues its steady march, but the universe they leave behind begins to speed up. Hours for them could be centuries for Earth. A civilization might rise and fall in the time it takes them to take a single breath. This is the ultimate consequence of gravitational time dilation, a reality so warped that a single moment near the black hole stretches into an eternity for the rest of the cosmos. Imagine a clock falling toward the event horizon. Each tick, each second, takes longer and longer to reach our telescopes, until that final tick before the horizon is stretched across all of future time, never quite arriving. The astronaut becomes a fossil, a living snapshot from a distant past, forever immortalized on the threshold. Yet for them, the fall continues unabated. They do not see the future of the universe flash before their eyes. Instead, they are utterly isolated, cut off from the cosmic timeline they once knew. This dramatic disconnect reveals a profound truth about our universe. Time is not a universal constant that ticks the same for everyone, everywhere. Its flow is shaped by gravity and motion. A black hole is a natural laboratory where these relativistic effects are pushed to their absolute limit. The slowing of time is a direct pointer, a signpost deep into the hole's core where the warping becomes infinite. How does this progression end? What lies at the very center where the river of space and time flows into its final destination? This relentless inward flow of space and time culminates in the singularity. At the very heart of a black hole, all the matter that ever crossed the event horizon is crushed into a single point. This point has zero volume, yet it contains a staggering amount of mass. The result is a place of infinite density, where the very concepts of space and distance break down completely. According to the equations of general relativity, the curvature of spacetime here becomes infinite. The fabric of reality, stretched to its absolute limit, develops a tear. In this state, the tools we use to describe the universe, our trusted laws of physics, simply stop working. The idea of a before and an after loses its meaning as time itself is predicted to cease. we are left with a mathematical boundary, a point where our understanding of nature hits a wall. It is fortunate this singularity is locked away behind the event horizon, hidden from our universe. This cosmic censorship shields the outside cosmos from the paradoxical storms raging within. Yet, this protection also denies us a direct view. How can we study something that lies beyond the reach of our most fundamental theories? The answer may lie not in the physics of the immensely large, but in the physics of the incredibly small. The key to unraveling this mystery could be waiting in the quantum realm, where different rules govern reality. The equations of general relativity point toward an infinite collapse at the singularity, but nature may abhor such a finality. This is where our other great pillar of physics, quantum mechanics, enters the stage, and the two theories find themselves in a fundamental clash. Quantum theory governs the bizarre, probabilistic world of the very small, where particles can be in two places at once and empty space is a seething sea of potential. When we try to apply the smooth, geometric rules of general relativity to the heart of a black hole, the math simply breaks down. The infinite densities predicted by Einstein's theory are a signal that we are missing a crucial piece of the puzzle, a piece that must come from the quantum realm. Instead of a single, infinitely dense point, the very center of a black hole might be a turbulent, frothing region physicists call quantum foam. At these unimaginably small scales, spacetime itself may lose its smooth character, bubbling with fluctuations where tiny wormholes and baby universes continually form and vanish. This chaotic foam could provide a pressure that halts the complete collapse, preventing the true singularity and offering a more complete, though far stranger, picture of the core. The need to resolve this conflict is the single greatest unsolved problem in theoretical physics, the quest for a theory of quantum gravity. One of the most tantalizing clues in this search came from Stephen Hawking. He realized that the void of space is not truly empty. Pairs of virtual particles, one with positive energy and one with negative energy, constantly flicker in and out of existence, usually annihilating each other too quickly to be measured. But what happens when this quantum dance plays out right at the edge of a black hole's event horizon? If one particle of the pair falls across the boundary while the other escapes, the black hole effectively loses a tiny amount of energy. To an outside observer, it appears as if the black hole is emitting a faint glow of radiation, now known as Hawking radiation. This slow, steady leak of energy implies that black holes are not entirely black and, more profoundly, that they may not be eternal. Over staggering spans of time, a black hole could slowly evaporate, its mass bleeding away into the cosmos as this quantum whisper. This remarkable idea connects the infinitesimal world of quantum particles to the vast gravitational domain of black holes, offering a first glimpse at how a unified theory might work. How does this slow evaporation change the ultimate fate of the matter and information that fell inside? The answer could redefine our understanding of reality itself. This slow leak of energy from a black hole is one of the most profound discoveries in modern physics. Stephen Hawking realized that black holes are not the eternal prisons we once thought. Due to the strange rules of quantum mechanics, they can actually evaporate. The process begins in the seemingly empty space just outside the event horizon. Here, pairs of virtual particles constantly flicker into existence, borrowing energy from the universe for a fleeting moment before they meet and annihilate each other. But at the precipice of a black hole, this delicate dance is torn apart. One particle of the pair can be captured by the black hole's immense gravity, falling across the event horizon, while its partner escapes into the vastness of space. To balance the cosmic books, the particle that escapes carries away a tiny amount of energy which is taken from the black hole itself. This steady trickle of escaped particles is Hawking radiation. Over timescales that dwarf the current age of our universe, this process causes the black hole to slowly lose mass, shrinking until it potentially vanishes entirely. A black hole with the mass of a small mountain would radiate away in a span of time roughly equal to the age of our universe, while a colossal one born from a dead star would take trillions upon trillions of years longer. This introduces a fundamental unpredictability into the heart of these cosmic giants. If a black hole can fade from existence, what happens to everything it once contained? This question leads us directly to one of the most heated debates in all of science, a puzzle that threatens our very understanding of reality, the black hole information paradox. This slow evaporation of a black hole leads to a devastating puzzle for physics. If a black hole can vanish, what happens to all the information it ever swallowed? Quantum mechanics, the rulebook for the subatomic world, has a golden rule. Information cannot be truly destroyed. It can be scrambled, changed, or hidden, but never erased from the universe. Think of a book. You could burn it to ashes, but in principle, a being with perfect knowledge could reconstruct every word from the precise arrangement of the smoke and ash particles. The information is preserved, just in a different form. Now imagine tossing that same book into a black hole. According to general relativity, the book is gone, crushed into the singularity. Its information lost behind an event horizon that eventually evaporates into a faint mist of featureless radiation. This creates the information paradox, a direct conflict between our two most successful theories of reality. One says information is eternal, the other says it can be permanently deleted. How can both be true? The stakes could not be higher. If information can be lost, the entire logical foundation of quantum physics collapses, and with it, our ability to predict the future state of the universe. This is not just about a lost book, it is about whether the universe operates on predictable, consistent laws. To find a way out, physicists had to reconsider the very nature of the black hole's surface. Perhaps the event horizon is not a simple one-way membrane. What if it acts more like a cosmic projector screen? This is the heart of the holographic principle, a revolutionary idea suggesting that all the information about everything that falls into a black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, like a hologram storing a three-dimensional image on a flat surface. The book story is not erased, it is painted onto the surface of the black hole itself, one bit of information per tiny, fundamental unit of area. As the black hole evaporates via Hawking radiation, this encoded information could slowly and chaotically leak back out into the universe, preserving the cosmic balance sheet. This idea ties directly to another profound concept, black hole entropy, a measure of disorder that hints at the hidden structure within these seemingly simple objects. The idea that a black hole has entropy at first seemed like a contradiction. Entropy is a measure of disorder, the number of hidden microscopic states a system can have. A scattered deck of cards has high entropy, while a neatly stacked deck has low entropy, but a black hole, according to classical physics, was the ultimate in simplicity. It was defined by just three things: its mass, its electric charge, and its spin. It had, as the saying goes, no hair, no other distinguishing features. So how could something so simple be associated with such immense disorder? The breakthrough came when physicist Jacob Bekenstein realized that entropy was not about what was inside the black hole, but about the information it hid. The event horizon, the point of no return, acts as a mask. When you toss an object into a black hole, it vanishes from our universe. All the intricate information about that object, whether it was a perfect diamond or a pile of dust, is lost to the outside world. This act of hiding information is a tremendous increase in disorder. Bekenstein proposed that a black hole's entropy is proportional to the area of its event horizon. The larger the surface area of this cosmic veil, the more information it can conceal and the higher its entropy. This was a radical shift, linking the geometry of spacetime directly to the statistical concept of disorder. Stephen Hawking initially disliked this idea as it seemed to violate thermodynamic laws. If a black hole has entropy, it must also have a temperature. But how could a black hole, a perfect absorber, have a temperature and emit anything? Hawking's own calculations on radiation provided the stunning answer. The slow, quantum mechanical glow we now call Hawking radiation is a thermal process. A black hole does have a temperature, and it is inversely related to its mass. A colossal black hole has a temperature barely above absolute zero, while a tiny, evaporating one would be intensely hot. This completed the picture, showing that black holes are not cold, dead relics but dynamic thermodynamic objects that obey and enrich the laws of physics. The profound connection is this: thermodynamics, the science of heat and work, emerges from the statistical behavior of countless tiny parts. For a box of gas, this is the motion of molecules. For a black hole, the parts are believed to be the fundamental, indivisible units of spacetime itself on the tiniest possible scale, the Planck scale. Each tiny square on the event horizon surface, a Planck area in size, may hold one bit of information like a single pixel on a cosmic screen. This is the holographic principle in action, suggesting that the three-dimensional reality we perceive inside the black hole could be a projection from a two-dimensional surface encoded with quantum information. Why is this bridge between gravity and heat so profound? It gives us a new language to describe the most extreme objects in the cosmos, a language rooted in quantum information and statistics. It suggests that spacetime itself may not be fundamental, but may emerge from a deeper, more basic layer of reality, much like temperature emerges from the motion of atoms. This thermodynamic view of black holes provides our most solid bridge toward a final theory of quantum gravity. Yet, this deep complexity hidden behind the event horizon stands in stark contrast to their outward appearance. From the outside, black holes remain incredibly simple, defined by just a few parameters. This is the essence of the No-Hair Theorem, a concept that makes these cosmic giants both understandable and deeply mysterious. This cosmic simplicity is captured by a powerful idea known as the No-Hair Theorem. It states that a black hole, for all its fearsome power, is defined by just three numbers: its mass, its electric charge, and its spin. Everything else is erased. Imagine two black holes with identical mass, charge, and rotation. One was born from a collapsed star made of pure hydrogen, while the other devoured entire planets, asteroids, and complex molecules. According to this theorem, these two histories are completely undetectable from the outside. They are perfect cosmic twins. The intricate details of everything that fell in, the chemical compositions, the atomic structures, all that information is lost behind the event horizon. The black hole presents a perfectly smooth, featureless face to the universe, a mask of ultimate simplicity. This theorem is a direct consequence of the elegant equations of general relativity, which seem to demand that black holes are the most efficient shredders of information in existence. Yet this very simplicity creates a stark tension with the story told by quantum mechanics and thermodynamics. Quantum physics, with its concepts of entropy and information preservation, suggests the interior, or at least the surface, of a black hole is a seething cauldron of complexity, storing bits of data on its event horizon like a vast cosmic hard drive. So which picture is correct? Is the black hole a simple, bald object as general relativity insists, or is it a complex, information-rich system as quantum theory implies? This contradiction is not a flaw in our theories, but a guiding light, pointing toward a deeper truth about gravity and reality. The No-Hair Theorem's elegant simplicity sets the stage for an even more dynamic and strange object, a black hole that is not just massive, but spinning at a significant fraction of the speed of light. But the serene simplicity of a non-spinning black hole is a cosmic rarity. In the violent chaos of the universe, most black holes are born spinning, and this rotation transforms them into even more bizarre engines. These are Kerr black holes, and their core is not a point but a ring, a singularity spinning so rapidly it flattens into a loop. This ring is a gateway to places beyond our universe, but crossing it is a journey into the unknown. The spin warps the spacetime around it so severely that it creates a region outside the event horizon called the ergosphere. Here, the fabric of reality is dragged along with the black hole's rotation, like a powerful cosmic whirlpool. Nothing can stand still, forced to move with the swirling spacetime. This relentless motion holds a remarkable secret. It allows for the extraction of the black hole's own rotational energy. Imagine a particle entering this ergosphere. It splits in two, with one fragment carrying negative energy falling into the black hole. To conserve energy, the other fragment must rocket away with more energy than the original particle had. This is the Penrose Process, a way to literally steal energy from a spinning black hole. The black hole pays for this energy robbery by slowing its spin, a small price for the universe to power its most energetic events. The effects of this spin reach deep into the nature of time itself. Time dilation near a Kerr black hole becomes even more extreme and complex, twisted by the frame dragging of the ergosphere. Your clock would not just slow down, its rate would depend on which direction you were moving, with or against the current of spinning space. The interior structure is a labyrinth of infinite possibilities, with theoretical gateways to other universes or distant points in our own, though these remain firmly in the realm of mathematical speculation. Studying these spinning giants gives us our most accurate picture of the black holes we actually observe, as almost every one detected shows signs of significant rotation. Their dynamic nature sets the stage for the most violent events in the cosmos, collisions where spacetime itself rings like a bell. The violent spiraling dance of two black holes does not unfold in silence. It sends tremors across the cosmos, ripples in the very fabric of spacetime itself. These are gravitational waves, a phenomenon predicted by Einstein a century ago and finally confirmed in 2015 by the LIGO Observatory. When two black holes circle each other in their final moments, they whip spacetime around them like spoons stirring a cosmic pond. As they draw closer and finally merge, they release a staggering burst of energy in the form of these waves, a brief, invisible storm that travels at the speed of light. The signal picked up by our detectors is a rising chirp, a cosmic song that tells a detailed story. The pitch and amplitude of this chirp reveal the black hole's masses, their spins, and the ferocious dynamics of their collision. It is through these ripples that we can study the nature of objects that emit no light, listening to the echoes of their formation. The final, fading ring-down of the wave after the merger is especially telling. It is the sound of the new, larger black hole settling down, its event horizon vibrating like a struck bell. The frequency and decay of this ring-down are pure probes of the black hole's properties, a direct test of how spacetime behaves under the most extreme conditions imaginable. By studying these vibrations, we are indirectly probing the mysterious core, testing whether the predictions of general relativity hold true or if subtle deviations point toward new physics, perhaps even a glimpse of quantum gravity at work. This new window into the universe allows us to observe the dark hearts of galaxies in a way light never could. Each collision we detect is a laboratory for the most extreme physics, offering clues about the singularities or quantum structures that might lie within. The echoes of these cosmic crashes lead our imagination even further to theoretical bridges that could connect distant points in space and time. These theoretical bridges through spacetime are known as wormholes. Imagine the universe as a vast, two-dimensional sheet of paper. A wormhole would be like a tunnel connecting two distant points on that sheet, a cosmic shortcut. This idea is not pure fantasy. It emerges directly from the equations of Albert Einstein and his colleague Nathan-Rosen, who found that the mathematical description of a black hole could be extended to form a bridge, an Einstein-Rosen bridge, linking it to another point in spacetime. This bridge would not lead into the black hole's crushing singularity, but out into another region of the cosmos, or perhaps even into a completely different universe. The exit point from this tunnel is theorized to be a white hole, a region of spacetime that, unlike a black hole, allows nothing to enter and only expels matter and energy. While we have never observed a white hole, and they may be mathematically unstable, their concept completes a beautiful symmetry in the fabric of reality. Yet holding a wormhole open for travel presents an immense challenge. According to general relativity, the throat of the tunnel would pinch shut instantly, crushing anything that entered. To prop it open, you would need a truly bizarre substance, exotic matter, which possesses negative energy density and negative pressure, effectively pushing spacetime apart against its own tendency to collapse. Whether such matter exists in usable quantities is a deep mystery. The implications of a stable wormhole are staggering. It would not merely be a tool for instantaneous travel across the galaxy, it would be a time machine. The different rates at which time passes at each mouth of the wormhole, due to gravity or motion, could create closed paths in time, allowing for travel into the past. This immediately raises profound questions about causality, the fundamental law that cause must precede effect. Could you travel back and prevent your own birth? The paradoxes are dizzying, and most physicists believe the universe possesses some as yet unknown mechanism, a cosmic censorship that prevents such logical inconsistencies from occurring. While traversable wormholes remain a speculative dream, their study stretches our understanding of what is possible, revealing the incredible flexibility hidden within Einstein's theory of gravity. This very flexibility, however, leads to another, more urgent paradox that strikes at the heart of our understanding of the event horizon itself. This smooth passage through the event horizon is a cornerstone of general relativity, yet it may be the very assumption that breaks our understanding of physics. The Firewall Paradox ignites a fiery debate at this boundary. To resolve the information paradox, some theorists proposed a radical and violent alternative, that the event horizon is not smooth at all. Instead, it could be a searing wall of high-energy particles, a literal firewall that would instantly destroy anything attempting to cross. An astronaut, expecting to fall peacefully into the abyss, would instead be vaporized by an unimaginable blast of radiation. This is not a gentle quantum whisper, but a cosmic inferno. The existence of such a firewall directly challenges Einstein's principle of equivalence, which assures us that a free-falling observer should detect nothing unusual at the event horizon, no dramatic barrier, no sudden heat. The universe, according to his theory, should look the same from that falling frame of reference. The firewall forces a brutal choice. Either the principle of equivalence is wrong, meaning general relativity fails at the horizon, or quantum mechanics is wrong, and information is truly lost. Neither option is palatable. This paradox reveals a deep and fundamental tension in how quantum fields behave in the severely curved spacetime around a black hole. The vacuum of space itself, that sea of virtual particles, may not be able to smoothly reconcile the perspectives of an outside observer and someone falling in. For the outside watcher, information is encoded on the horizon, but for the falling astronaut, there is nothing there but empty space, until perhaps there is everything, a wall of fire. This debate is not merely academic, it is a battle for the soul of physics, forcing us to question which of our most cherished principles must be rewritten to describe reality completely. If such a destructive boundary does exist, what does that mean for the matter it consumes? As we follow the path inward, we must now ask what remains of anything after it encounters this potential inferno, and what form it takes as it journeys toward the mysterious core. This cosmic inferno at the event horizon is a theoretical possibility, but we can actually observe black holes feeding in a spectacularly violent display. Far from being passive vacuums, black holes actively devour their surroundings. When a star drifts too close or a cloud of gas is captured by the immense gravity, the material does not fall straight in. Instead, it forms a vast, swirling whirlpool around the black hole known as an accretion disk. Like water spiraling down a drain, this gas and dust orbits at tremendous speeds, friction heating it to millions of degrees. This superheated plasma glows with an intense, blistering light, often in the high-energy X-ray part of the spectrum. It is this brilliant, hot disk that allows us to see the unseeable, revealing the presence of an invisible monster at its center. The energy released in this process is almost beyond comprehension. When a black hole feasts on a steady diet of material, the accretion disk can outshine every star in its host galaxy combined. These cosmic engines are known as quasars, and they are among the most luminous objects in the entire universe. A single quasar, powered by a supermassive black hole, can be 1,000 times brighter than our entire Milky Way galaxy. This is the great paradox of black holes. They are defined by their darkness, yet they can create the most brilliant beacons in the cosmos. The process of accretion is not just a light show, it is how black holes grow. Every particle of gas, every shredded star that spirals into the event horizon adds to the black hole's mass, increasing its gravitational pull and the size of its event horizon. This growth shapes the environment on a galactic scale. The intense radiation and powerful jets that often erupt from the poles of an accretion disk can blow away surrounding gas, halting the birth of new stars and effectively regulating the evolution of an entire galaxy. The way a black hole eats tells us about its history and its future, but what controls the flow of material into this cosmic drain? The answer lies in invisible lines of force that twist this swirling maelstrom into shape. These brilliant accretion disks are often shaped by invisible architects, powerful magnetic fields generated by the swirling, superheated plasma. Like cosmic particle accelerators, these fields can launch colossal jets of matter, shooting straight out from the black hole's poles at nearly the speed of light. These are not gentle streams but furious beams of energy that can stretch for thousands of light years, far beyond the boundaries of their home galaxy. In systems like the famous Cygnus X1, we observe this dramatic process in action. The black hole's intense spin, combined with the churning motion of the accretion disk, twists the magnetic field lines into a tightly wound coil. This creates an enormous slingshot effect, channeling some of the infalling material and hurling it back out into the cosmos along the only path of least resistance, the rotational poles. This is how a black hole, a creature of ultimate consumption, becomes one of the universe's most powerful engines of creation. The energy in these jets can carve vast bubbles in the intergalactic medium, heating surrounding gas and preventing it from cooling to form new stars. In this way, a single black hole can dictate the growth and ultimate size of its entire galaxy, a tiny heart with a galactic reach. These jets also contribute to the cosmic rays that constantly pepper our planet, high-energy particles from the most violent events in the universe. This magnetic complexity forces us to look even deeper, beyond the classical singularity. As we probe the theoretical core, some physicists propose that a complete theory of quantum gravity might replace the infinite point with a Planck star, a hypothetical object where matter is compressed to the smallest possible scale, the Planck length, creating a rebound effect rather than an endless collapse. This suggests the black hole's core could be a place of immense yet finite density, a temporary state in a much longer cosmic cycle. The violent brilliance of a black hole's accretion disk points toward a hidden engine, but the true nature of that engine remains a mystery. What if the core is not a point of infinite density, but something else entirely? A radical idea from the theory of loop quantum gravity proposes that the singularity is replaced by a Planck star. This is not an infinitely dense point, but a region of space compressed to the highest possible density allowed by the quantum nature of reality, the Planck density. At this scale, the fabric of spacetime cannot be compressed further. Instead of collapsing forever, the matter and energy at the core would rebound, creating a powerful outward pressure. Think of it as a cosmic bounce. A star collapsing into a black hole would not vanish into a singularity, but would be squeezed into this tiny, ultra-dense Planck star before beginning a slow, outward expansion. This process resolves the troubling issue of the mathematical singularity, a place where our physical laws break down. By replacing the infinite with an extremely large yet finite density, the Planck star model offers a complete picture that avoids the dead end of a singularity. This quantum bounce happens deep within the black hole, completely hidden behind the event horizon. For most of the black hole's life, the event horizon remains, and to the outside universe, it appears as a classic black hole. But the interior is not a one-way street to oblivion. It is a place of temporary confinement, holding a bouncing core in a state of suspended animation. The most profound implication concerns the fate of information. If the core is a Planck star that is slowly bouncing back, then the information about everything that fell into the black hole is not lost forever. It is preserved within this quantum structure, waiting for its eventual release. How could that information ever escape? The answer lies in the black hole's incredibly long life. Over trillions of years, as the black hole evaporates through Hawking radiation, its mass decreases and its event horizon slowly shrinks. According to this model, the moment the shrinking horizon reaches the expanding Planck star inside, the black hole would effectively cease to exist. The trapped energy and information would be released in a final, spectacular burst, a cosmic rebound echoing across an ancient, dark universe. This offers a potential solution to the information paradox, suggesting that information is not destroyed but merely stored for an almost unimaginable duration before being returned to the cosmos. This quantum gravity perspective transforms the black hole from a destructive end into a phase of matter, a temporary resting place for energy and information. Yet, this vision of a bouncing core is not the only radical reimagining of a black hole's nature. Another theory suggests that the entire three-dimensional interior is an illusion, a projection from a flat, two-dimensional surface encoded with information. This idea that reality might be a projection is the heart of the holographic principle. It suggests that all the information needed to describe the three-dimensional world inside a black hole is not truly inside at all. Instead, it is painted like a cosmic tattoo onto the two-dimensional surface of its event horizon. Each tiny unit of area on this boundary, a square of the smallest possible size, holds one fundamental bit of information. The swirling stars, the clouds of gas, the very fabric of space and time that fell in, all of it is encoded there. A black hole, in this view, is the ultimate hologram. The rich, three-dimensional reality we imagine within its dark heart is just a projection, a shadow cast by the intricate data vibrating on its spherical surface. This resolves the information paradox with breathtaking elegance. When a black hole evaporates via Hawking radiation, it is not deleting information. It is slowly and chaotically reading out the data stored on its surface, releasing the scrambled story back into the universe. The information was never truly lost, just transformed and stored in a different dimension. This principle reaches far beyond black holes, hinting that our entire universe might operate on the same fundamental rule. The world you see and feel, with its depth and solidity, could be a holographic projection from a distant, two-dimensional surface at the very edge of the cosmos. This bridges the chasm between gravity and quantum information theory, suggesting that spacetime itself is not a fundamental building block, but an emergent property, a collective behavior of countless bits of quantum information. How does this profound encoding of information relate to the raw power black holes wield over their surroundings? The data stored on the event horizon is not passive. It is intimately linked to the black hole's gravitational influence, which in turn sculpts the evolution of entire galaxies. These supermassive black holes are more than just occupants at the center of galaxies. They are cosmic architects, their immense gravity and explosive energy shaping the destiny of their stellar cities. Our own Milky Way hosts a relatively quiet giant, Sagittarius A star, a silent sovereign whose presence is felt more through its pull than its voice. But in other galaxies, the central black hole is a roaring engine, and its influence is direct and profound. The relationship is a delicate dance of creation and destruction. Vast clouds of gas, the raw material for new stars, are drawn toward the galactic center by the black hole's gravity. Yet, as this gas spirals inward, forming a brilliant accretion disk, the black hole unleashes a torrent of radiation and channels powerful jets of particles from its poles. This energy output acts as a global thermostat. The intense heat and shock waves can blow the surrounding gas away, or keep it so agitated and hot that it cannot cool down and collapse to form new stars. A black hole can paradoxically quench star formation, preventing its galaxy from growing too large too fast. How did such a powerful feedback mechanism arise? The evidence suggests that black holes and their galaxies grew up together in a process of coevolution. The galaxy feeds the black hole, and the black hole, in turn, regulates the galaxy's growth. Their fates are intertwined, a gravitational partnership written across billions of years. This grand cosmic choreography, observed from afar, raises a pressing question. How can we possibly study the precise details of an object that traps light itself? The shadow of a black hole is not an empty silhouette. It is a profound darkness cast against the glowing backdrop of its own accretion disk, a cosmic signature we can now see for the first time. The Event Horizon Telescope did not take a simple photograph. It orchestrated a global symphony of radio telescopes, from the high deserts of Chile to the peaks of Hawaii, synchronizing their observations with atomic clocks. Together, they formed a single, virtual observatory the size of our entire planet, a feat of engineering necessary to glimpse the shadow of the supermassive black hole known as M87 star. The technique is called Very Long Baseline Interferometry, and it allows us to resolve details with stunning precision, equivalent to reading a newspaper in New York from a sidewalk cafe in Paris. The result was that now iconic image, a fiery ring of light surrounding a dark central region. This dark heart is the black hole's shadow, a region roughly 2.5 times larger than the actual event horizon. It is not the event horizon itself, but the shadow it casts, a gravitational lensing effect so extreme that light from behind the black hole is bent around it, tracing a perfect circle of fire. The shape and size of this shadow are a direct test of Einstein's theory of general relativity. A distorted or misshapen shadow could have hinted at new physics, a crack in the century-old foundation. Yet the image revealed a shadow that was remarkably circular, precisely matching the predictions for a spinning black hole described by the Kerr solution. This mathematical description of a rotating black hole, derived from Einstein's equations, had long been our best model. Now we had visual proof. The image of M87 star confirmed that the object at its center is indeed a Kerr black hole, a spinning vortex of pure gravity. It provided the first direct measurement of its mass and its spin orientation, offering a real-world anchor for theories that were once pure mathematics. This was not the end of the story, but the beginning of a new era of observational black hole physics. Each new observation, including the image of our own galaxy's central black hole, Sagittarius A star, adds another data point, another piece to the puzzle. What other secrets will these dark circles reveal as we learn to read the subtle variations in their fiery rings? The mathematics that predicted these shadows now guides us deeper toward understanding the very nature of the spacetime they warp. The mathematical architecture of a black hole is written in the language of differential geometry. To understand these cosmic objects, physicists turn to specific solutions of Einstein's field equations, elegant blueprints that map the warping of spacetime. For a perfectly still black hole, the Schwarzschild solution provides the model, describing a simple, spherical geometry with a central singularity hidden by its event horizon. But since most things in the universe spin, the Kerr solution is far more relevant. This model describes a rotating black hole, where the singularity is not a point but a ring, and the spin drags the very fabric of spacetime around with it. At the heart of these solutions lies a mathematical object called the metric tensor. Think of it as a complex, multi-dimensional ruler that tells you how to measure distances and intervals of time in a severely curved landscape. It calculates how spacetime stretches and compresses, dictating the path that everything from light to planets must follow. These equations are not just abstract symbols. They are the tools that allow us to run simulations on supercomputers, visualizing the gravitational lensing that creates a black hole's shadow or the violent ripples in spacetime when two black holes collide. By solving these complex differential equations, we can predict the precise location of an event horizon or the intense time dilation near it, testing the limits of general relativity against real-world observations. This mathematical foundation is absolutely crucial. It provides the stable ground from which all theoretical leaps are made, including the speculative journey into one of the most elusive concepts in all of physics. What if the relentless pull of a black hole has a theoretical opposite, a place where nothing can ever enter? This theoretical opposite of a black hole is known as a white hole. If a black hole is a cosmic drain from which nothing can escape, a white hole is a cosmic fountain from which nothing can enter. It is a region of spacetime that violently expels matter and energy, but allows nothing, not even light, to cross its boundary inward. The mathematics of general relativity, in its beautiful symmetry, allows for such an object. In fact, the same equations that describe a black hole can be run backward in time to describe a white hole. They are, in a sense, time-reversed twins. One endlessly consumes, the other endlessly erupts. While we have never observed a white hole, and many physicists believe they may be mathematically unstable or impossible to form, their concept completes a profound picture. In some models, a black hole's interior singularity might not be a dead end, but a bridge, an Einstein-Rosen wormhole, that connects to a white hole in another part of our universe or in a completely different universe altogether. This suggests a breathtaking topology for spacetime, where these strange objects could be two sides of the same cosmic coin. How would such a structure fit into the larger universe? The matter and energy pouring from a white hole would not be random. It would be the same material that fell into its connected black hole, potentially scrambled and transformed, but fundamentally preserved. This offers another potential route to resolve the information paradox, suggesting that what a black hole consumes in one region of reality, a white hole might give back in another. This directly challenges our everyday understanding of cause and effect. If information can travel through such a tunnel, does the cause, the act of falling into the black hole, still precede the effect, the emergence from the white hole? Or could the sequence be reversed from a different perspective? Exploring these hypothetical objects forces us to stretch our notions of causality to their absolute breaking point. As we contemplate these cosmic reversals and the extreme warping of spacetime, we must also consider the invisible forces that dominate our universe. The same framework of general relativity that predicts black and white holes also guides our understanding of dark matter and dark energy, the mysterious components shaping the cosmos on its largest scales. The same invisible hand that shapes the cosmos may also sculpt the darkness around a black hole. Dark matter, the unseen substance that makes up most of the mass in the universe, does not interact with light, but it is not immune to gravity. Around a supermassive black hole, vast halos of this mysterious material could accumulate, creating a deep, invisible well of gravity. This hidden reservoir could fundamentally alter a black hole's environment, funneling regular matter more efficiently into its accretion disk and accelerating its growth over cosmic time. The subtle gravitational pull of a dark matter halo might even leave faint fingerprints on the orbits of nearby stars, stars that seem to circle an emptiness far greater than the black hole itself. These interactions turn black holes into unique natural experiments. By observing how a black hole grows and how objects move in its vicinity, we can infer the properties of the dark matter that must be there, even though we cannot see it directly. Does the dark matter simply fall in, or could it become so densely packed that it creates its own unique effects? This connection bridges the immense scale of cosmology with the extreme physics of black holes, offering a new way to probe the universe's greatest unseen component. This search for understanding, for using the most extreme objects to answer fundamental questions, inevitably leads us to reflect on our own place in the cosmos and the responsibilities that come with such knowledge. These cosmic paradoxes ultimately lead us to a profound and humbling question about our own reality. Black holes are not just astronomical objects, they are philosophical crucibles, forcing us to confront the very meaning of time, cause and effect, and existence itself. The timeless nature of a singularity, a place where our understanding of a before and after dissolves, challenges the linear flow of time we take for granted. What does it mean for something to happen if time itself has stopped? This questions the foundation of causality, the principle that every effect must have a cause. In the twisted spacetime around a black hole or within a hypothetical wormhole, these clear sequences can become tangled, suggesting that the universe's logic might be far more flexible than our everyday experience allows. These puzzles naturally lead to speculative ideas like the multiverse, where our universe is just one bubble in a vast cosmic foam. with every black hole a potential gateway to another reality with entirely different physical laws. Such concepts stretch the imagination, pushing science into realms once reserved for philosophy. This partnership is essential, for philosophy provides the framework to ask the big questions that our equations cannot yet answer. It encourages us to consider not just how the universe works, but why it might be this way and what our role is within it. This line of inquiry brings a deeply human dimension to the cosmic scale. Could life ever exist in the brutal environment near a black hole? While the region immediately outside the event horizon is scoured by intense radiation and gravitational forces, more distant orbits might be possible. A civilization advanced enough might harness the immense energy of the accretion disk, or even use the black hole's extreme gravity as a lens for interstellar travel. Their view of the cosmos would be unlike our own, watching the rest of the universe speed up in a dizzying fast-forward while their own time crawled by. Such a perspective would fundamentally alter a culture's understanding of its place in the cosmos, blending astronomy with existential meaning. The study of black holes, therefore, is more than a scientific pursuit. It is a journey that merges the empirical with the philosophical, forever changing how we see ourselves in the vast, mysterious tapestry of existence. The violent environment around a black hole seems the least likely place for life to take root, yet the universe is a place of profound contradictions. Far from the event horizon, in the outer reaches of a black hole's gravitational domain, a stable orbit might be possible for a planet. This world would be locked in an eternal dance with darkness, its primary source of energy not a star, but the brilliant, swirling maelstrom of the black hole's accretion disk. This superheated plasma could provide the light and heat necessary for a sun, casting an unending, flickering daylight upon the planet's surface. The conditions would be bizarre and unstable, with the disk's brightness fluctuating wildly, but within that chaos, a narrow band of possibility could exist. Another, more subtle source of energy could also nurture life. The same tidal forces that would spaghettify an object falling too close could, at a safer distance, gently flex and heat a planet's interior through constant gravitational kneading. On a world with a subsurface ocean like Jupiter's moon Europa, this internal heat could maintain liquid water away from the hostile surface, creating a sheltered environment where life might emerge in total darkness, warmed from within by the black hole's relentless pull. The feasibility of such ecosystems is a thrilling thought experiment for astrobiology. It forces us to expand our definition of a habitable zone beyond the warmth of stars. Life around a black hole would be a testament to tenacity, clinging to existence in a realm of extreme physics. It suggests that the ingredients for life might be sown in the most unexpected of cosmic gardens, forever changing how we search for our place in the universe. This expansion of possibility pushes our scientific ambitions further, demanding new tools and new visions to explore these dark frontiers. The next generation of observatories will listen to the universe in frequencies we have never before been able to hear. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will open an entirely new window on the cosmos. Unlike its ground-based counterparts, LISA will consist of 3 spacecraft flying in a perfect triangle millions of miles apart, connected by laser beams. This colossal instrument, floating in the quiet of space, will be free from the seismic rumbles and thermal noise of Earth, allowing it to detect the lowest frequency gravitational waves, the deep bass notes of the universe. These are the waves produced by the most massive objects, like the slow, stately dance of supermassive black holes as they spiral toward collision in the hearts of distant galaxies. Ground-based detectors have given us the chirps of stellar mass black holes merging. LISA will give us the full symphony of these galactic giants, a rumbling crescendo that can last for years, tracing their orbital decay with exquisite precision. This will allow us to test Einstein's theory in the most extreme gravitational fields with unprecedented accuracy, potentially revealing subtle deviations that point toward new physics. What happens when spacetime is stretched to its absolute limit? The data from LISA could provide the first direct clues. Alongside these new ears, we are building new eyes. The next wave of extremely large telescopes, with mirrors spanning the width of tennis courts, will use advanced adaptive optics to peer through Earth's atmosphere with crystal clarity. They will track individual stars orbiting perilously close to our galaxy's central black hole, Sagittarius A, mapping its gravitational field in minute detail. These observations could reveal subtle distortions in the star's paths, hints of the invisible structure of spacetime around the event horizon, or even evidence of the dark matter halo that must surround it. The sheer volume of data from these instruments, a deluge of information measured in petabytes, presents its own monumental challenge. This is where artificial intelligence becomes an indispensable partner. Machine learning algorithms can sift through this cosmic noise, identifying faint gravitational wave signals buried in the data, or spotting subtle patterns in the flickering light of accretion disks that would be invisible to the human eye. These AI systems are not just tools for analysis, they are becoming partners in discovery, capable of finding correlations and anomalies that might take human researchers decades to uncover. They help us simulate the complex, violent mergers of black holes, modeling the warping of spacetime and the resulting gravitational waves to compare directly with what we observe. This powerful synergy between human curiosity and machine intelligence is pushing the boundaries of what is knowable. With these advanced tools, we are no longer just observers of black holes, we are becoming active listeners and interpreters of their hidden language. These artificial minds are now sifting through the cosmic static, finding signals in the noise. Machine learning algorithms process petabytes of data from telescopes and supercomputer simulations, searching for subtle patterns in the flickering light of accretion disks or the complex ripples of gravitational waves. They act as tireless research partners, capable of spotting correlations and anomalies that might take a human scientist a lifetime to find. For instance, the same technology that powers facial recognition is helping to refine the iconic image of the M87 black hole. Advanced algorithms filled in the gaps between the global network of radio telescopes, sharpening our view of that fiery ring. In simulations, AI models the chaotic flow of plasma in an accretion disk, predicting how magnetic fields twist and snap to launch those colossal jets of energy. This is not about replacing human curiosity, but amplifying it. By handling the immense computational heavy lifting, these systems free researchers to ask bigger, more profound questions. How will this partnership evolve? We are entering an era where machine learning could autonomously classify new types of celestial events or even propose entirely new theories to explain the data it collects. This powerful alliance between human intuition and artificial intelligence is transforming our cosmic exploration, turning raw data into profound understanding. The journey to grasp these enigmatic objects has not only reshaped science, but has also captured the human imagination in powerful ways. These dark cosmic giants have leaped from the pages of physics journals into the heart of our collective imagination. For decades, films and books portrayed black holes as terrifying monsters, voracious voids reflecting our deepest fears of the unknown and of being consumed. They were the ultimate cosmic threat, an inescapable fate for any spaceship that strayed too close. This narrative began to shift as our scientific understanding deepened. Modern stories, like the film Interstellar, attempted a more nuanced portrait, blending real scientific consultation with human drama. Its depiction of a spinning black hole, Gargantua, with its brilliant accretion disk and profound time dilation, was not just spectacle, it was a gateway for millions to ask genuine questions about relativity and the nature of time. Art and cinema hold up a mirror to our curiosity, transforming abstract equations into relatable human experiences. They give form to our awe, allowing us to stand at the edge of the infinite from the safety of a theater seat. This cultural journey from fear to fascination mirrors science's own path, moving from seeing these objects as destructive ends to understanding them as dynamic engines that shape the cosmos. The stories we tell about black holes are ultimately stories about ourselves, exploring themes of exploration, sacrifice, and the relentless human drive to understand where we come from. Reflecting on this journey, we can now gather the profound lessons these enigmatic objects teach us about the universe. They have shown us that space and time are woven into a single, malleable fabric, a fabric that can be curved, stretched, and even torn. They have forced us to confront the unsettling idea that information, the very essence of reality, might be preserved in ways we are only beginning to comprehend, perhaps encoded on a two-dimensional surface like a cosmic hologram. Black holes have unveiled a deep and fundamental conflict between our two greatest theories, general relativity and quantum mechanics, a conflict that points toward a deeper, unified truth about gravity and the quantum world. They have taught us humility, revealing that our common-sense understanding of time as a universal constant is merely a local phenomenon, shattered near an event horizon where one person's moment is another's eternity. Most of all, they have revealed that the universe is far stranger, more flexible, and more wonderfully bizarre than we ever could have dreamed. The study of black holes is not a niche pursuit. It is a fundamental quest to read the deepest rules of reality, written in the dark heart of gravity itself. These cosmic paradoxes and profound puzzles all point toward a handful of overarching principles that redefine our place in the universe. Black holes serve as our ultimate teachers, revealing gravity not as a simple force, but as the very curvature of spacetime itself. They show us that under extreme conditions, the rules we take for granted, like the steady flow of time, are merely local customs in a far more flexible cosmos. The relentless pull toward the singularity underscores the limits of Einstein's theory of relativity, a framework that works perfectly until matter is compressed beyond all comprehension. It is at this breaking point that we confront the urgent need for a deeper theory, one that can marry the vast scales of gravity with the fuzzy probabilities of the quantum world. This quest for quantum gravity is perhaps the most important lesson of all, a reminder that our understanding of reality is still a work in progress. Even the stunning simplicity of a black hole's external description, defined only by its mass, spin, and charge, hides a universe of internal complexity, suggesting that what we see is often just a mask for a richer, hidden structure. These insights collectively paint a picture of a cosmos that is far stranger, more interconnected, and more wonderfully bizarre than we ever could have conceived from our small corner of the galaxy. The journey to understand these dark hearts is far from over. With every new observation and every theoretical breakthrough, we peel back another layer, forever pushing the boundaries of the known and venturing closer to the ultimate secrets of space, time, and existence itself. Black holes stand as one of science's most thrilling frontiers, a place where the universe's deepest laws are written in the dark. Their mysterious cores challenge everything we think we know about time and space, pushing the very rules of physics to their absolute breaking point. The great Stephen Hawking once offered a brilliant correction to our imagination, reminding us that black holes are not as black as they are painted. They are not static voids but dynamic, evolving entities, glowing with a faint quantum whisper and capable of shaping the destiny of entire galaxies. This ongoing journey of discovery, from the event horizon to the quantum foam, connects directly to a fundamental human impulse, that deep-seated curiosity about our place in the cosmos. It is the same wonder that makes us look up at the stars and ask why. If this exploration into the heart of darkness has sparked your own sense of awe, consider subscribing for more journeys into the universe's greatest mysteries. We would love to hear your thoughts and questions in the comments below. Together, let's keep unraveling the enigmas of space and